good morning, good afternoon, or good evening, wherever you are located. The geology of New England can be very complex, and the overview that I'm going to give is going to be primarily concentrated on its relation to groundwater. About 500 million years ago, the continent of Pangaea was formed, and what is important is that the North African plate collided with the North American plate. The first example of that are the Berkshires and the related deposits on the borders with New York and Connecticut and Vermont. What is most interesting is that we have limestone and marble deposits, which are unrealistically formed at the latitude that now exists, except that when our portion of the North American continent was being formed, New England was in fact below the equator. Next, as the continent started to pull apart and to separate, the Connecticut River was formed, and we have information in the next slide showing, in fact, what it looks like today, and where the deep blue is suggesting the parts of the ocean that may in fact be deepest. This is an example, obviously, of a lava flow. We have no examples that we can count to in New England. In fact, if there had been much in the way of volcanic activity, subsequent erosion has removed it. Another example of what may or may not have ever taken place in New England. However, what is most important, that as the continents pulled away, large fractures were developed at different parts of New England, and they do play an important part in whether you are developing a sand and gravel well or something in the underlying bedrock. Here we have an example of a fracture that is moving at an oblique angle. You can see the darker deposits here, which is a dike. And this is an example of what we look for in New England. Hopefully at the later time, I'll discuss in rock wells. Okay, we have a lot of granitic materials, igneous materials in New England, gabbros, felsites, but granites are one of the major components of the underlying bedrock. Here we're talking about near the very top of a batholith, where in fact granitic material has intruded into the overlying bedrock, however has not broken out on the surface. Well, what is most important to us in New England on and with regard to the development of high yielding bedrock wells, about 2.5 million years ago, it started to freeze. The temperature dropped between 5 and 10 degrees, and in Labrador, ice started to form, which did not melt during the summer. Eventually, it's estimated that a thickness of close to 3 miles of ice was developed. With this amount of weight, the bottom part had a certain plasticity, and it started to flow southwards. Now, we know that there are definitely 5 times in the last 2.5 million years that ice has completely covered New England. However, I have heard recent estimates, it may be as high as 17 glacial events have taken place. However, each subsequent event may have destroyed some of the evidence of what preceded it. Here's an example of multiple mountain glaciers flowing into a major one. What is of interest to us is the dark bands, which is the material that has been ingested into the ice, bedrock, previous existing soils, even organic debris. Example again of a glacier advancing, in this case into the ocean. And lastly, as the glacier moved forward, it pushed debris in front of it, much like a bulldozer. A glacier never advances in one push and does not retreat in a single push. There are advances, stagnation, more advance, partial retreat, more advances. Well, here we're looking about something that is quite interesting. As the glacier widened and deepened the valleys, the material ingested into the ice was then deposited during the glacial retreat. And here we have several examples that may be of interest. You'll notice that we have blocks of ice right here. As sand and gravel being released from being ingested in the ice is swept around these, that when it later melts, it will be left as a depression forming a kettle hole. And around kettle holes, the potential for sand and gravel deposition with what would appear to be water developing transmissive sediments may in fact be possible. An example again of a glacier in retreat. Please notice on either side, as a glacier retreats, it shrinks in from the sides and down from the top, but in fact you can get coarse sand and gravel deposits on the side of the valley. All right, this slide is very important because we are seeing subsequent deposition at multiple points during this retreat. Over on the left-hand side, you will notice that a stream is coming out beneath the ice. This is carrying very coarse sediments that ultimately, when covered as the glacier retreats further up the valley, may in fact represent a favorable zone to develop a public or high-yielding well supply. It continues to prograde further on out with the sediments getting finer until we have a glacial lake in which clay deposits are going to be found. This will account for how we can end up within a glaciated valley with sediments that are totally different at different points within the valley. All right, here we have what ultimately is going to become an esker. This particular stream at the bottom here has a high velocity and is going to be carrying very coarse sediments. To get an idea of the size, I can't see it, up here on the right-hand side is a person who is about this high, just to give some perspective as to the size of what will ultimately become an esker as the ice melts and the coarse deposits here are left within the valley. Here we're talking about characteristic of a valley that has been glaciated. You'll notice a U shape. Again, we're talking about what has deposition. The valley itself is markedly deeper to the underlying bedrock. Cartoon here showing exactly what's going on. If you'll notice clearly, here was a stream beneath the glacial and ice putting an esker. Drumlins, and I will explain this in a little bit. We have a terminal remain. I indicated that we advance forward, pushing material. This would be Glacial Till, and here is an outwash plain, something that again we look forward to finding because the potential for a high yielding well exists in that type of deposition. Here we have Glacial Till, which drillers call hardpan. This is material which was laid down beneath the ice. It goes anything from clay particles through silt, sands, and in fact, boulders. Now there are two types of till. If the glacier stagnates and the ice melts down and the material within is just deposited beneath the ice, then in fact it's an ablation till. However, if we are talking about something that is laid down as the glacier in fact has thousands of feet of ice on top of it, it is much denser. And this becomes somewhat important because in the development of bedrock wells, in many cases, it is overlain by glacial till. If you have an ablation till, more water can be stored within it and it can dewater into the underlying bedrock fractures more effectively. Here we have an outwash plain. And as you can see, during the summer, there is much more melting going on. And in this particular case, it probably was a warm summer with much deposition going on. A moderate winter, a very cold summer, by an even colder winter. So that this is the type of material that in sand and gravel deposits will in fact be potential for a high yielding well. All right, this particular slide is very important because if you dig at the surface, you have nothing but coarse, clean sand and gravel. However, please note that if you put in a test well right in this location, you are not going to find anything, and yet moving a short distance away, there are very coarse sediments that in fact, when saturated, would yield a whole lot of water. Something right in here would yield a lot of water, but there and the other side there will not. That is why you can never be sure with a singular test well that in fact you have found something that could be developed most effectively. This is the spring runoff in the Pemigewasset Valley in northern New Hampshire. This is the type of deposition that would be quite similar to what in fact would end up being an outwash plain. But note, you have very coarse material right here, but in this particular area right there, you have the deposition of fine material all taking place simultaneously. Here we have what is less of an esker. Obviously, this had been a tunnel beneath the ice of a glacier, but even at this distance, you can see how coarse and clean the sand and gravel is. Eskers are one of the important features that we look for in the development of high-yielding wells. This is an esker that actually was in a lake. The source of recharge is quite obvious, but this particular well that was drilled right there had the potential to yield 3 million gallons per day, which is a very high yielding well in New England. And to get an idea of the perspective, this is Franconia Notch in northern New Hampshire. This is the Pemigewasset River, and you can see the deposition of very coarse material that if the glacier was still in the location right here, would cover up this material, which in fact can transport a large amount of water. Now here we have a drumlin, where this is composed of basal till. Why in itself it is not a potential source, it is used by communities for site right on the top, water towers. This is approximately 3/4 of a mile in length, 1/4 of a mile in width, and approximately 300 to 400 feet in elevation. However, on the southwest and southeast quadrants of drumlins, there in many cases are deposits of permeable sand and gravel deposits. If anybody has any questions, we're ready to answer them.
Hi, Ted. We actually do have a couple of questions. One is, can you talk about the difference between basal and ablation tills and talk about how much water each type of those tills could produce?
As a matter of fact, most tills are only good for old dug wells for a single family. We're talking 1 or 2 gallons per minute, and most of these, in fact, go into the very upper regions of the groundwater table. so that the ablation till is less dense than a basal till, but neither is particularly of any benefit to develop a high yielding well.
Great, thanks for that. A follow-on question to that is why are eskers, kettle holes, and outwash plains good spots to look for high yield wells?
The reason that they are is they're mostly comprised of well-rounded, clean sand and gravels, in many cases devoid of finer sediments, which would block the interstices or voids between the individual particles. Therefore, groundwater can move through those deposits rapidly, making them very good sources for potential high-yielding wells.
Great, thanks. And we've got one other one. How important is detailed superficial geologic mapping for siting large yielding water supplies?
Superficial mapping is going to be beneficial because it is going to help you in several ways. Number one, it's going to show you what the potential for the underlying saturated settlements will be, but also you should be able on that mapping to look up gradient to make a determination how much watershed is up gradient to provide recharge. Also, if you look closely at areas up gradient, you can rule out sites where there may be potential for uh, materials that dumps would be example, or landfills, any up gradient farming that may elevate nitrogen. And you can also take a look and see, is there any industrial activity or roads that could degrade water quality.
Great, thanks for that. We've got one other question on one of the images that you showed. The person is asking, how did you, in the second to last slide, determine that there was an esker at the location? So I think if you back up a couple slides when you were talking about eskers.
That particular shot was taken right next to Interstate 95, 495 in Boxborough, Massachusetts, which is one of the major mapped eskers in the state of Massachusetts. So that it's clearly identified by the contours that is an esker.
Great, thank you. And so that's all we've got for questions right now. So I'm going to go ahead and pass things back to you. Thanks.
Here we have an indication of what is typical in New England. Water table unconfined aquifers are most prevalent. We do not have much in the artesian with a confining layer overlaying it. As a matter of fact, I would say that of the wells developed by my company, 95% would be in the unconfined saturated material, and less than 5% would be in the confined layer, and which is true artesian. We still find that the old technology of drive and wash is the least expensive and the most effective way to determine what the stratigraphy is within a area that we believe sand and gravel potential for development of groundwater exists. Here we're talking about a bombardier mounted drilling rig with a hammer being raised and lowered that will drive 2.5-inch diameter Schedule 80 steel pipe into the ground. Here's a coupling going on the bottom. The Schedule 80 pipe has an outside diameter of 2.75 inches and an inside diameter of 2.33. Here we're talking about a 350-pound hammer, which is being raised and lowered approximately 30 inches to drive the 2.5-inch casing into the material. Water is now jetted into the casing, which has an open bottom to flush out the sediments that in fact will lodge within the casing. That water comes out flushed and is dropped into a bucket where it is captured. It is graded for color, it is graded for transmissive capability, and the coarseness and the description of the sediments which are being flushed out. Color is important in New England. We have found that gray sediments have a tendency to have elevated concentrations of soluble iron and manganese, whereas brown sediments have a tendency to be lower concentration to none of those two metals. This is approaching what we call refusal. Refusal may be either the underlying bedrock or dense glacial till. I have only 4 examples where till has ever been underlain by permeable sediments, and in those cases, it has been a flow till. The till itself became saturated and flowed over on top of permeable sediments, and then a readvance of the glacier overlaid the till with sand and gravel, which is clean. Here's an example of when we look at the log of the sediments that have been penetrated, we will select a test screen. A screen itself is a series of vertical rods around which is wrapped trapezoidal water and wire, and the open area in thousandths of an inch is the slot size. Therefore, something which would be 10 1/10 of an inch would be a 100 slot screen. The typical screens used in most test wells are between 40 and 100 slot. Now, this is an example of what the advantage is between a wire wound screen on the left and a shutter screen on the right. The shutter screen has much less open area, and the fact that it is a lip is more difficult to develop to maximize the yield of the test well. The well is developed using a diaphragm mudsucker pump, which has a pump pause. After the water has been dislodged, a column of water falls back down the test well, turning over the formation so that more fine material, finer than the slot size of the screen, may be brought close to and dislodged. We are trying to get a jacket of coarse, clean gravel larger than the slot size of the screen adjacent to this test screen itself. Here we are pumping it with a centrifugal pump. And what we are noting, first of all, what is the static water level? How far beneath the ground is, in fact, the water table? That is going to account for what the inches of vacuum on the very top of the well. This becomes important. If in fact this pumps 40 to 50 or 60 gallons per minute, we will move 2 linear feet away and drive an observation well to the same depth as the test well. Here we may choose to put a different slot size screen in, usually coarser. Of the 2 wells, whichever pumps the higher capacity, we will then run a pumping test of 2 to 4 hours in duration, noting the GPM of the test well, the inches of vacuum, and what the drawdown is within whatever has become the observation well. This will give us a preliminary specific capacity of that particular stratum from which we can project upwards what the ultimate yield of a permanent well may be capable of producing. There's a test well log, which in fact is going to describe on the left-hand side the different stratum, their thickness. It also is going to give an indication of whether wash water was lost. Good indication. If you lose wash water, it will probably give wash water. We note the color as indicated before, which is important because we may give up some potential yield to develop a shallower stratum, which may in fact have better water chemistry. The duration of the pumping test would be noted and what the total drawdown in the observation well would be. Also, it should be noted how quickly after the pumping is curtailed does it recover back to the original static water level. Well, this is an example of one of the methodologies used to run and conduct the pumping test, which is usually the second stage after a favorable test well has been found. Rather than putting an 8-inch or 12-inch diameter test well in the center, if it is particularly shallow, more water can be pumped by putting in a group, usually a hexagonal group with one observation well in the center to check what the drawdown is going to be. However, we can also put in an 8 or a 12-inch well. Now, I had indicated that we usually put in a test well and 2 foot away an observation well. However, in Auburn, Massachusetts, we put in the test well. It did 40 gallons per minute. We moved 2 feet away and put in an observation well that only pumped 15 gallons per minute. We moved and put in an observation well 2 feet away on the opposite side that pumped 60 gallons a minute, and then moved and put in the 8-inch well at this location 2 feet from here, and it pumped 200 gallons per minute. If in fact this had been the original test well, the town of Auburn, Massachusetts would never have ended up with a public water supply cited here. There are different types of drilling machines that can put in permanent wells and the test well. This happens to be a dual rotary barber machine, which has the capability to spin casing and also has a drill bit in the center. If in fact you have a cobble complex or encounter a boulder, this piece of machinery can drill through it. And in fact, in North Kingstown, Rhode Island, using this piece of equipment, we were able to go through a 10-foot diameter boulder into permeable sediments beneath it, and we were able to develop a well that pumped 1 million gallons per day. This is the type of material that we're looking for. If you look closely, we're talking medium to coarse sand with fine gravel and cobbles. You will notice there is no indication on the person holding any evidence of fine sand, clay, or silt. And again going back to make an indication, in New England now, shutter screens are almost never used. They still may be utilized for irrigation wells in the Midwest and out in the mountain states. The advantage being that the shutter screen is far less costly than the wire wound screen. Here we have an example of a well that would be typical of a test well in the intermediate stage. It is not gravel packed. The natural sediments are coarse enough that in fact development can pull through what is obviously shown here as finer sediments through, ending up with a jacket of coarser material. This is called a telescope screen. The OD of the telescope screen is slightly smaller than the ID of the well casing above it. All right, conducting a pumping test. You have to be able to take the water being pumped and discharge it far enough away that in fact it is not going to be able to come back and provide recharge overinflated the potential capacity of the well. Wells can be pumped with a suction lift pump if they are shallow, But remember, a suction lift centrifugal pump can only draw water from a depth as deep as 24 feet beneath the surface. So in a very shallow aquifer, a pumping test can be conducted with a suction lift pump. However, in deeper wells, most are now conducted with a submersible pump powered by a generator. Here we have an example of a shallow aquifer. This is going to be a tubular well field, 50 feet on center. A series of small diameter wells are manifolded. This is the pumping test, and to a suction manifold, to a suction pump, and the discharge is being run up and out of the particular basin. So shallow aquifers certainly are still potential high yielding sites. Our company just rebuilt a well field for the Brunswick Topsom Water District in Brunswick, Maine. There were more than 50 of the small diameter wells, and the ultimate yield is going to be 800 gallons per minute. What is important is when you are conducting a pumping test is to accurately measure the flow. Many times it's done by an orifice weir right at the point of discharge, where the weir will restrict the flow, causing in a tube on the side an elevation to come up, which is measured. There are tables that will predict exactly what the yield will be. Also, you want to be able to take the discharge water onto a sheet of plywood that we have jokingly called an energy dissipator, and keeping a Concom happy, surrounding it by sand hay bales so that there will be no erosion. We're back to potential questions.
Do have a few of those. One is, are there scenarios where a well should not be installed in a sand and gravel terrain?
The answer being yes, if in fact you know that the water chemistry is going to be of such a poor state that in fact it would cost too much to in fact build a treatment facility for it. Now this could be if you are proximal to swamps, or now called wetlands. The closer you are to those type of surface supplies, the greater the likelihood that your groundwater is going to have elevated iron and manganese. Again, I mentioned before, farms, you have the problem of animal waste. You also have the problem that there may be a rare and endangered species of some sort, that if in fact you pump that sand and gravel deposit at the desired maximum rate, you are going to have an adverse impact upon those. And lastly, some pollution can come from very long distances. Example, if your sand and gravel deposit overlies a major fault, it is possible that pollution can move as much as a couple of miles away, so that you have to be very knowledgeable of what is going on. Most people do not think that sand and gravel deposits derive recharge from the underlying bedrock. That is incorrect. There is a distinct relationship between the overburden and the underlying bedrock.
Great, thanks for that. A couple other questions we have coming in. One is, has sonic drilling been used successfully in sand and gravel terrain?
Yes, it has. As a matter of fact, sonic drilling, again, if you have reason to believe you are going to have major boulders and or cobble complexes that the 2.5-inch diameter driven well cannot penetrate, the sonic rig is certainly something that is excellent. Also, in fact, that if your static water level is going to be below 24 feet, a sonic rig will allow you to put in a 4 or 6-inch diameter test well that you will then be able to put a submersible pump in and make an accurate evaluation.
Great. One other question that we have is, would you ever put an observation well closer than 2 feet to a test well?
No.
Okay.
Eh,
Good to know.
what you don't know, you know that they're 2 feet apart on the surface. What you don't know is, well, it's 80 or 90 feet deep, what in fact it is going to be. The closer it is, the more misleading the potential specific capacity is going to shown to be, which in fact is going to give you incorrect information.
Thank you. And that's all the questions we have for this section.
Until about 50 years ago in New England, drilling a rock well was pretty much a hit or miss scenario. The problem being is that we had no methodology available to make a determination where zones of fractured bedrock may be. Obviously, this example, if you randomly sited a well and drilled right here, you had the potential of getting a much higher well capacity than if you went either side. The USGS in New England has stated that if you throw a rock over your shoulder backwards, you have a 98+% chance of getting sufficient water to take care of a single home. However, less than 10% of all wells randomly sited will do 10 gallons a minute, and less than 1/2 of 1% will do 50 gallons a minute or greater. As I indicated, that most of the bedrock in New England is primarily igneous or metasediments, sedimentary rocks which have been metamorphosed. We have very few deposits of sedimentary rocks such as sandstones or conglomerates, and we have very few deposits of limestones. Therefore, the crustal fracturing of the Earth's crust has to prevent fractures, which will allow groundwater to be stored and to be yield. If in fact you drill and don't hit any of these fractures, you are not going to get a well that is going to produce much water. Here's an example of what may be a moderately yielding well. It has encountered one fracture. Here we have an example of what we hope to find if we're looking for a high yielding well within the underlying bedrock. This is an example of one of the type of fractures that we hope to encounter. This particular one is near Route 128 in Massachusetts, and you can see the number of vertical fractures that are existing. Not only does this store water, but it moves at a potential to have a high velocity. Well, how do we determine where these are? Dr. Parizak at Penn State, now 45 to 50 years ago, started plotting high yielding bedrock wells. And he found out there was a linear or a curvilinear feature to them, which he was able to associate being zones of highly fractured bedrock. Now, directly over these zones of highly fractured bedrock, the flora is going to be different. If the bedrock table is close to the surface, you're going to find that large uh, trees with deep bedroot are able to be able to intercept the groundwater table more easily. But this may be a zone where groundwater is and surface water is draining into the fracture matrix, and the material growing here is going to be stunted more than what is on either side. Well, using aerial photography, you can do fracture trace or lineament mapping and try to identify these features. And when in fact they are identified, you look for an area where multiple fractures converge at a single location. This is advantageous because your odds of intercepting fractures that are going to yield water is increased, but also you are going to be able to induce recharge from multiple points of the compass. And plotting this up, it is obvious that drilling at this location right here is going to give a markedly higher likelihood for a favorable high yielding bedrock well than if you drilled at any of these points not in any way associated with the identified linear features. Now, when you are going through this identification process, you obviously have to take a look at any anthropogenic activity that may account for it. Fences, roads, paths, pipelines, anything like that would have to be dismissed, and what is left has a high degree of probability of being a zone of fractured bedrock. If you are doing a town-wide study, you take a look and see where each of these identified areas might be, and then you take a look and say, if a high yielding well is there, where is the source of recharge going to be? Is it going to have an adverse impact upon existing wells or any of the other activities that in fact are using groundwater or surface water? There may be times when you are drilling a rock well that you encounter fractures which are unstable. It is rare, but there are times when a well screen has to be put in that section of instability in order to make sure that a pump is not locked in by debris falling on top of it, or in fact enough debris falls in that in fact you reduce the yield. Here's a typical rock well. In New England, we have to have a seal of neat cement usually, so that a driller will start off oversizing a hole and then will put casing at least 15 feet into competent bedrock. When the casing is sealed in place, then a smaller diameter bit is usually drilled down to see if in fact fractures are encountered and what the preliminary water chemistry may be. If in fact it then turns out that the yield may be potentially greater, you have the opportunity to ream the well out to the diameter of the steel casing. And the way that you do a preliminary idea of what the yield is, because you are pumping with compressed air, is to set a pipe of a certain diameter inside a small dam, and from the invert to the elevation of the water will give you a preliminary gallons per minute. Time for questions.
And we've got a few coming in, actually. One question is, what are the advantages or disadvantages to having a bedrock well versus a sand and gravel well?
Well, the advantages are number one, there may be no sand and gravel, or the sand and gravel has been maxed out and that you are not going to be able to develop any more. The second is that in cases where the fractured bedrock is overlain by glacial till, you might be able to set up something where during times of drought, you pump from the bedrock wells, knowing that you are not in any way going to have an adverse impact upon surface water bodies, be it a pond, a lake, or a stream.
Great, thanks for that. We've got a couple other questions. One is, could you discuss the extent to which glacial sediments cover fracture traces? Specifically, don't glacial deposits mask underlying fracture traces?
Normally, that would be a very logical interpretation. However, that has not turned out to be the case. We are somewhat amazed that you are able to pick up fractures beneath some areas of till. Now, if you're talking 200 or 300 feet, the likelihood that it is going to mask it. However, you may in fact be able to determine a linear feature, and then nothing is shown, and then on the other side of a valley where there's a thinner overburden, it picks up again, and you can surmise that those two straight features are in fact connected beneath the area where it becomes difficult to identify a specific linear connection.
Okay. And that's all the questions we have for now.